first met Dror in January of 2026, it must have been. 60th birthday conference. But his influence has extended far beyond that. So this is convenient for me because I'm going to discuss link homology. So here is, in my mind, a somewhat famous handout of Dror's in his expository paper, which reformulates Khovanov-Homology. So this is from 2002. At the time this was written, I was 3 years old. So Dror's influence goes very far. This was the paper which was presented to me by my PhD advisor in order to learn some things about link homology, and doing professional mathematics had a great influence on me. I'll say also, Dror, by means of this paper, taught me the Reidemeister moves for the first time as well. So just to highlight some features of this construction, so we start with some link, planar diagram of the link. And then there's this famous cube of resolutions construction where you take each crossing and you resolve it in terms of these two different arcs. So you either resolve it sort of perpendicular to the crossing or perpendicular in the other direction to the crossing. You get this collection of planar diagrams. And then there's some over both this quantum dimension, so each of these diagrams represents some graded vector space, and this homological direction as well. And this produces some categorification of the Jones polynomial. So to recover the Jones polynomial from this construction, you take the graded dimension of the graded vector space indicated in this picture, and then take its Euler characteristic, which is to say the alternating sum of the dimensions in each homological degree. Now, there's a generalization of this story due to Khovanov-Rozansky to general type A Lie algebras. So the input for this story is a link, which maybe has several components, and some type A Lie algebra, GLN. And the output is once again a bigraded vector space, maybe the type AN Khovanov-Rozansky homology. And when n equals 2, you recover the Khovanov homology. And there's a further generalization of this story, which sort of unifies all of these homological invariants in the same way that the Homfli polynomial unifies all the GLN Reshetikhin-Turayev polynomials. This is called the Homfli homology. It's now a triply graded invariant. And the input is again a link, which is now presented not as some planar diagram arbitrarily, but as a closure of some braid diagram. And the output is some triply graded vector space, where now there's this extra variable A, sort of like the A variable in the Homfli homology, in the Homfli polynomial. To give an example, so say we have the trefoil law. How do you actually describe this invariant? Well, it's some triply graded vector space, and so you can record its dimension as some 3-variable power series, which records the dimension of the piece in each tri-grading. So for example, if you take the trefoil and you look at its graded dimension, this is what you get. Now, this is some power series. I've written it as a rational function. You can think of this denominator 1 minus q squared as being some formal expansion of 1 plus q squared plus q to the 4th, etc. So really, this is some big direct sum of some finite dimensional pieces shifted in degree by 2 in the q direction. And when you set t equals minus 1, which corresponds to taking alternating sums in the homological direction, you recover exactly the Homfli polynomial of the trefoil in these conventions. Now I'll say for homology, there's some common change of variables here into these capital letters, which just collects expressions which appear very often in the Homfli homology. So I'll use capital A, capital Q, and capital T throughout. So here's the dimension of the Homfli homology of the trefoil in these variables. And now to recover the Homfli polynomial, you simply set t equals q. So the early development of Homfli homology was pretty dramatically influenced by these conjectures of Dunfield, Gukov, and Rasmussen in 2005. One of the conjectures was that Homfli homology exists. So you'll notice the dates here is that the way it happens, these conjectures sort of predate the construction of triply graded homology by Khovanov and Rozansky. But what they conjecture is a finite dimensional version of this. And you'll notice that all these expressions are infinite dimensional due to this denominator as well. So really, these conjectures address the reduced Homfli homology. They also conjectured that there were some spectral sequences which started at Homfli homology of a given knot and eventually converge to the type AN Khovanov-Rozansky homology of that knot. These were constructed by Rasmussen in 2006. And they also conjectured spectral sequences to many other link invariants. So for example, there's the hat version of Knot-Heggard-Flirt homology. And there's a big gap between this conjecture and the proof of this conjecture. This is 17 years, so this paper inspired a great deal of mathematics to this day. They also conjectured spectral sequences to these new GL minus n homologies, and these have begun to appear in the literature over the last 10 years or so. But I would say this is very much still a work in progress. And to back up their conjectures, they gave many exact predictions for porous links. So this package of structural properties on Homfli homology together with some knowledge of the Khovanov homology of these torus knots and links, enables you to pin down exactly what the dimension of the Homology homology should be, and all of these conjectures have since panned out for torus links. So these conjectures are rather well known, but there's another package of conjectures from about 13, 12 years ago, which I think is not as well known as it should be. So I want to outline these conjectures for you now. These are due to Gorsky, Gukov, and Stosic, and also another follow-up paper by Gukov, Nowata, Saberi, Stosic, and Shulkovsky. And these are very similar to the DGR conjectures, but they concern colored Homology homology. So what colored Homology homology is, it's again a triply graded invariant of links, but now each link component is colored by some additional data. In this case, it's going to be some partition. For the GGS conjectures, it's a rectangular partition, but this encodes some stable representation of the type A Lie algebras. And they conjecture, again, more spectral sequences to these new GLMN homological invariants, where here GL11 should specialize to Hegardt-Fleur knot homology. There's some progress on this front, though not for spectral sequences. They conjecture some mirror symmetry property involving the interchange of the Q and T variables, so something like the Jones and the homological degree have some symmetry here, which is unexpected. They conjecture also some exponential growth in the partition size, which we'll discuss in a moment. Most strikingly and titularly for the GGS conjectures, they conjecture that the triple grading on Homology homology actually refines to a quadruple grading at the colored level. And this is completely open. It's perhaps the most tantalizing of all these conjectures. If anyone has truly any ideas at all, I would love to hear them. There was some follow-up work as well, which extended the above conjectures to links, not just knots, and more general partitions. And there's some color shifting conjectures as well. I'll describe some progress on this front later in the talk. And I'll say for both, again, there were many exact predictions for torus links. So if you want to start to prove these things, you can calibrate your expectations against some data for torus links. So to compute any of this data, you need some models of colored homology. So let me come back to this slide in just a moment. So first, let me describe for you what sort of colored homology actually exists. So here I'll restrict the case to the partition being a single column. This corresponds to the representation wedge K of SLNs and goes to infinity. And here there are many different models you can consider. So they're all going to start with this colored braid. Remember, Homology homology takes a braid presentation of a link. And here I'm going to label each component of the braid by this exponent K. So this is, for instance, the wedge 2, wedge 3 colored Hopf link. Now you can resolve this braid into something which resembles a cube of resolutions called a Rickard complex, and then apply some functor which computes homology, and this will give you what's known as the intrinsic Homology homology. But there are other things you can do as well. So this description sort of categorifies the Moy calculus description of colored Homology homology. But there's other descriptions by Morton and Aston using the Heck algebra and certain idempotents in that Heck algebra. And these descriptions of the Homology polynomial involve cabling the link first and then inserting certain idempotents to color each component. And these descriptions categorify as well. So, for example, for any partition of 3, say 2, 1 or 1, 1, 1, you can take a corresponding cable of that link component and insert some complex which accomplishes the coloring for you. And this also gives you some colored Homology homologies. Now there's one more thing you can do, which is if you first choose a base point on your link, then you can consider the reduced homology corresponding to that base point. So this requires a little bit of auxiliary data, but you can still do it. And this is an invariant of a choice of a component of a link and the link itself. And this gives you some invariant reduced colored Homology homology. So what I want to do next is just summarize some features of each of these invariants. So here are the big ones first. These are all infinite dimensional. So the intrinsically colored Homology homology, where you just take this cube of resolutions type thing. This is from 2008, 2009, and it passes through the Rickard complex, which is some bounded complex of singular Zergo bimodules, some algebraic gadgets. This is your analog of the cube of resolutions. One thing that's not so great about this is it's infinite dimensional, although it is finite dimensional in each tri-gradient, so the situation is not so bad. But it's hard to compute. So this was constructed in 2009, and when you bump the crossing count all the way up to 2, then the computations become very, very difficult. So this, for a general color on each component of the Hopf link, this was completed in 2021 in some very complicated work. So it's nice to have some alternatives. One such alternative is this projector colored homology, which mimics this cabling and insertion procedure for the Homology polynomial. This was constructed for general partitions in 2017. Here you can work with just non-singular regular old Zürich bimodules at the cost of working with infinite complexes. So this thing is again infinite dimensional, but it's finite dimensional in each trigrading. And the nice thing about this invariant is that there are recursions which compute this thing for positive torus knots. So I'll demonstrate those recursions for you in a moment, but the point is that we have some methods to compute this thing. And this middle colored homology, which I showed you, is sort of an interpolation between these two invariants. So these are the infinite dimensional ones. Now there's also this reduced homology. This was constructed by Paul Weidrich in 2016, with the restrictions that the choice of base point is on a component of minimal color among all the colors of the components of the link. And he also restricts to non-split links. So we refined this about a month ago in a paper on Archive to arbitrary links and arbitrary base points. And the idea here is when you choose a base point on a k-colored component, this gives you an action of symmetric polynomials in k variables on the Homology homology, and you just kill this action in some derived sense at the level of cubes of resolutions. One nice feature is that this invariant is finite dimensional for knots, and this matches with the GGS and GNSSS conjectures. So there's some hope, at least, that this is the invariant they were thinking of. On the other hand, it's quite difficult to compute directly, I think. So it's possible that this is not so hard as it sounds. I mean, everything here is finite dimensional. So if you're interested in this, I mean, there are programs which compute, say, uncolored Homology homology and Khovanov-homology and Khovanov-Rozansky type AN homology. So this is an open problem to write a corresponding program which computes this invariant for reduced Homology homology directly. Okay, so if the projector colored homology is easy to compute, and the reduced homology is what we're actually after to test these conjectures, then you need some way to compare between these various invariants. And I've spoiled for you on the handout what those comparisons are. So in a couple of papers over the past couple of years, I've constructed some functors which intertwine some of these constructions. And it turns out that these invariants are fairly closely related. So for instance, to pass from reduced homology to the intrinsically colored homology, you just have to tensor with the unreduced homology of a colored unknot, which corresponds to the color on which you reduced. So for uncolored Homology homology, this theorem is not so hard to prove. It was proven in Rasmussen's work, sort of implicit in the construction as well. For colored Homology homology, there's more to do, but indeed it turns out to be true. So these two invariants determine each other. And moreover, each of these partitions along which you cable the colored components are related to each other by some simple quantum integers. So here, this quantum 2, for instance, is the polynomial q plus q inverse, and you just multiply by this polynomial to pass between the dimensions of these. And this is true for arbitrary partitions as well. This is just an example. Great, so now we have a plan. We can use the recursions, which are sort of well known, to compute these invariants and then walk our way back up these comparison theorems. And this should, if everything goes well, give us some explicit computations for the reduced Homology homology of positive torus knots. So this is what I want to turn to next, starting with the computations of these invariants. So these computations were sort of kicked off in some sense by Elias and Hogenkamp in 2016. The techniques were refined by Mellett as well, and eventually this gave a computation of all row-colored positive torus knots and positive torus links. Here we're interested in column colors, but it turns out you can run their same procedure with only a few modifications. The first one is you have to do this thing called yification. This is some deformation of Homology homology provided by Gorski-Hogenkamp, and it turns out to be sort of the key to making all of this tick for links. The other thing is you take their symmetric colored complex, with which they color, which is their analog of this thing k, and you just replace it with the alternating colored thing, and you get some complex of this form. Now here, N, M, and L are not colors on the components. These are cables. So for instance, I have M strands going through here. Alpha V and beta W are some shuffle braids corresponding to some binary sequences V and W. And here's an example of such a complex. So here, if I take V equals 1100 and W as given, then the resulting complex you get is something like this. And you can check for yourself that this is exactly a two-colored, two-fold cable of the positive trefoil together with this this projector inserted. So if you could compute something for this complex, then you can understand the two-colored homology of the positive trefoil. So there are some recursions which compute the homology of such complexes. Here they are. It's sort of medium ouch. There's 8 rules. But they're indexed by these binary sequences together with some choice of permutation, which you have to track. It's not so bad. You can tell a computer to do these things, and it terminates in finite time, so that's rather nice. However, there's one simplification you can make, which is if you're interested in reduced homology, you're eventually dividing by all these normalization factors. Right? In particular, there's some conjectures in GGS which deal with the case when you set capital Q equals 1. And when you do such a thing, the recursion simplifies considerably. In particular, you can drop this permutation as well. And this recursion is a lot easier to deal with directly. And what this recursion does is computes for you directly the reduced wedge K-colored homology of some positive torus link TMN after you set Q equals 1, which is a bit strange. Q is like the original Jones parameter. So it's trained to set this equal to 1. I mean, A equals 0 makes sense, T equals -1 makes sense, but this is something new somehow. Great, so we have some recursion which computes these invariants. And let me just say there's some very concrete interpretation of this recursion. So you can treat your two integer sequences as like two decks of cards. There's sort of ones and zeros, which maybe correspond to red cards and black cards. And you can imagine somebody dealing these out and playing some game, and this gives you some nice probabilistic interpretation of the whole recursion, which I'll skip for now in favor of demonstrating this theorem. And what this theorem says is if you take the MN torus knot and color it by color K, then upon specializing Q equals 1 to give you some doubly graded polynomial, this records the dimension of its reduced Homology homology. This invariant satisfies some exact exponential growth. So if you take instead the one-colored invariant of the same knot, and you specialize Q equals 1, but you still have some two-variable polynomial, then there's exactly this exponential growth relation between the K-colored invariant and the one-colored invariant. So this is somewhat surprising. What's more surprising is the proof, which relies heavily on analyzing the orbits of the partitions involved in this complex. So there's some permutation here, some permutation here, and some permutation here. And you can track the orbits of these permutations as you run the recursion. Each step corresponds to some topological move. And that gives you a lot of information about the recursion. On the other hand, there's some very concrete description where permutations are nowhere in sight. So as a homework assignment, I would love to see some proof of this theorem directly without appealing to these permutations, which are auxiliary to the sort of reduced recursion. Great. So in the last few minutes, let me maybe demonstrate the program which we wrote up, which actually computes this thing. So here it is. It's in Sage Math. It's not so bad. You can find it on my website if you'd like to play around with it yourself. There's some preliminary stuff, which just packages all the things which Mathematica does for you for this metric group. Here's the main recursion, which breaks into a bunch of different rules. Nothing too surprising. And then there's some normalization at the end. Just run all this. Now to compute anything is not so hard. So here, for instance, you can compute the two-colored homology of the 3-4 torus knot. I also have here the two-colored of the 4-7 torus knot, a little bit bigger. And then there was some mention yesterday of the 22-7 torus knot. So let's see if we can't get the one-colored homology of that as well. And I'm running everything from scratch. Nothing is saved here. And it runs pretty quickly. So there we go. Just got 22-7. And here is the dimension of the 22-7. Oops.
Wait, but it's not a general program that runs for every knot, which is restricted to which is run on torus knot 22-7.
Yes, unfortunately, it only works for positive torus knots. Yeah. So this saves us a lot of work, but it also, costs us a lot of flexibility. But here's the invariant. We're going to be scrolling for a while. Okay. So in case you can't count very quickly, we can grab the rank of this thing as well. This is not so hard. Here it is. It's about, let's see, 1.5 million. And now you can also see the rank of, say, one-colored T34 versus five-colored T34. Here I see exactly 11 for one-colored and 11 to the fifth, which confirms the conjecture. Slightly larger knot, you can do T11.5. It's one and two colored variants. And here it is, 2033 and 2033 squared. An even larger knot, you can do T13.14, and this is the 14th super Catalan number, as expected. And then you can crank it up even larger. Here's some 2000 crossing knot. And indeed, you can compute the rank of this thing without too much difficulty as well. This runs very quickly. So I encourage you, please go to my website and fiddle with this program if you wish. One thing I would like very much is some prediction of how this invariant grows for knots of the form T2, 2n plus 1. So, so happy birthday, drawer, and thank you very much.
Questions?
Yes?
something which sounded understandable for outsiders were those red and black cards.
Yes.
Will you say a couple of words about it?
Yes, absolutely. So if you look at this recursion here, so you start with two binary sequences, sequences of zeros and ones. And there's some base cases, 1 and 2. But the bulk of this thing comes from just understanding what happens when you have various choices of final digits in each of these sequences. So for instance, here I see a 1 and a 1. And you can imagine having two decks of cards and flipping over two red cards, for instance. And so this, what this rule tells you is what to do when you flip over two red cards. You can imagine also if you flip over, say, a black card on a red card or a red card on a black card, there's some rule for what to do here. And then if you flip over two black cards, there's some rule for what to do also. So you can either replace sort of with a red card at the bottom of the deck, or with probability T, you can replace with a black card at the bottom of the deck. And then what you're computing is the probability of, say, every time you remove some ones, you collect those cards. What you're computing is the probability of collecting a certain number of pairs of red cards, up to some normalizations involving T goes to 1 plus T and A goes to 1 plus A. Yeah. So it's something very explicit, and there's no permutations in sight here. Nevertheless, this exponential growth proof relies heavily on the presence of permutations, so it would be great to eliminate this and deal directly with the recursion. Does this address your question? Great.
Okay, thank you.
More questions or comments? No, so please let's thanks again.